Hello, welcome to the first parallel session for JuliaCon. Our first speaker is Wolfhart Feldmeier from University Hospital of Vienna, and he will talk about differentiable rasterization of point cloud data. The floor is yours. Have fun.
Thank you, and also welcome from my side to this session. So this talk is about a package called DiffPointRasterisation, and this is a new package, my first one actually. It will end up in the general registry hopefully today, if all goes well. And as the name suggests, the package is concerned with the rasterization of point clouds in a way that is fully differentiable. So what do I mean with that? What do we mean by a rasterization of point clouds? So you basically have a set of points and you have a raster. So a raster is a regular rectangular grid in this case. So for example, in 2 dimensions, that would just be an image consisting of pixels. In 3 dimensions, you would have voxels and so on. And then for each point, you just find the correct bin and add the point's weight to that bin. So this example here shows the process basically. So you have a point cloud in yellow, an airplane that is 3-dimensional. You project it down to 2 dimensions, and then you put it in this very coarse raster for this example. So this is a 64 by 64 grayscale image. You basically fill the pixels with those points. So this process is basically just discretization of position information with maybe some projection in between. So almost by definition, this is not differentiable, right? It's discrete. It's not even continuous. So how can we deal with this? We can make it continuous like so. So consider a single point as shown in blue here. Normally with normal rasterization, you would take this point and just fill a single pixel with the point's weight. So in this case, this would fill the center pixel here. But what we do instead to make this continuous is we consider the nearest neighbor pixels. So we take the 2 to the power of n pixels that are closest to the point, where n is the dimension of the grid. In this example, we are 2-dimensional, so we have 4 nearest neighbors. And then we simply do a multilinear interpolation. The closer the point is to the bin center, the more weight it gets. If point and bin center fully overlap, then a single pixel still gets all the weight. So for this example, the resulting part of the image filled by this blue point then looks something like this in grayscale. As you can see, several pixels are now affected by a single point, and now it is continuous and actually piecewise differentiable. So just as a quick side note, so the effect of a single point is still very localized, so especially for very fine grids. So if you might want to follow up with a blurring operation, so individual points can feel a gradient from further away. Okay, but so how can we use the package to do this sort of thing? Essentially, a package offers a single function as an API. It's called raster, and it has several arguments. The first one being the size of the output grid. This is just an n-tuple of integers. So if this is a 2-tuple, then you will get a 2-dimensional image. If it's a 3-tuple, you will get a 3-dimensional image, and so on. Second is a vector of points, where each point is itself represented as a vector. And this is followed by parameters for an affine map. For example, this could be a rotation matrix and a translation vector. But it doesn't really have to be a rotation matrix, can be any matrix, and it doesn't even have to be square. So for example, you could also provide a rotation matrix multiplied with a projection matrix. The main point here is the dimensionality input as well as output is really arbitrary as long as this is consistent. So meaning basically if you put in an m-dimensional point cloud and your output should be an n-dimensional image or grid, then this linear transformation R needs to be an m by m matrix. That's all. Okay, so let's look at a quick example. So we want a 3-dimensional output that has 64 pixels in each dimension. So we plug in a 3-dimensional point cloud, our airplane here. So we need a 3-by-3 matrix. In this example, this is just a rotation matrix, and then we end up with a 3-dimensional image, image consisting of voxels. We can use the same point cloud as an input and raster it into a two-dimensional image. So therefore, we just provide a two-tuple as the size. But now we need to provide a matrix that projects down to 2 dimensions. So we basically pre-multiply this rotation matrix with a projection matrix, and then the output is a single image, very low resolution. Okay, there are other parameters that are optional, such as a weight per point. Then you can provide a background value per image and a weight per image. And I said per image here, but so far the output has always been a single image. So what's going on here? There's also a batched mode. So if you provide vectors of parameters instead of just a single set of parameters, then the output will have an additional batch dimension in the last position. So it has a trailing batch dimension. And of course, these vectors all need to have the same size. In this example, the length is 9. So you will end up with an array that has length 9 in the last dimension, basically representing 9 different images corresponding to these 9 different camera parameters, if you will. If you use batched mode on CPU, things run in parallel over different threads. So each image basically is running on its own thread, as long as there are enough hardware threads available, of course. On GPU, all points actually rastered in parallel. Okay, so far I've talked about the forward process, but as advertised earlier, the way the rasterization is done is differentiable, and it's actually differentiable with respect to all parameters, or at least with respect to all continuous parameters, all parameters except the first one, the size. So how do you actually use this in a differentiable program, right? So if you use a chain rules compatible automatic differentiation library, you don't worry about this at all. It just works. So you just use the raster function in your forward pass, as shown in this very simple example, which has a quadratic loss that uses the raster function in the forward pass. And then the reverse diff rules that are included in this package take care of the rest. So the AD system recognizes the reverse rules and basically provides you with the backward pass. And then you can access, like this example shows Zygote, right? You know how to use it. You can then access a gradient of this scalar loss functions with respect to the input parameters, like so. But there is also an explicit interface. So if you don't want to use automatic differentiation, and again, the interface consists of just a single function. It's called raster pullback. Done? It's called raster pullback. It looks like this. It takes the exact same set of arguments as the forward pass, but instead of the first argument being the size of the output, it takes the sensitivities of a scalar value with respect to the output of the raster function and pulls them back and returns the sensitivity of this scalar value with respect to the input parameters of raster. Okay. Yes, please.
So why did you choose to do this affine transformation for the user and not let the user decide what to do with points before throwing the points into your function?
Well, so the true answer is because, I mean, I used that in an application and I want it this way. But I also think, so, I mean, I want gradients with respect to, this linear transformation and the translation.
Yeah, but then it would be 2 lines of code in your loss function, right? So that would still be possible, or not?
Maybe I don't fully get the question. Can you maybe?
So you apply this affine transformation, RNT,
inside this function,
inside your function.
So you would do it outside.
Yeah, you could also do it outside and give your transformed function. So users could choose to do something else.
True. But yeah, so the thing is, so if you want to do this in a batched manner, right, then you will apply different transformations, And it's more memory efficient if you just provide a single set of points and a set of transformation parameters. Otherwise, you would, if you want to do this in a batched manner, then you would have to, you know, transform the whole point cloud in different ways.
Okay.
Yeah.
Thank you.
Okay, thanks.